It's my great pleasure and honor to introduce my dear friend and colleague, Sam Krevor. Sam is a professor and Royal Academy of Engineering Senior Research Fellow in the Department of Earth Science and Engineering at Imperial College London. His research group investigates issues of reactive flow physics and technology scale-up in application to subsurface carbon dioxide storage. He's an associate editor for the International Journal of Greenhouse Gas Control and was a 2022 and 2023 distinguished lecturer for the Society of Petroleum Engineers. Sam, he has also led a publication of a Nature Review article about the perspective on CCS and hydrogen, and we have the pleasure to have him here directly speaking about that also publication as well. Sam, please.
Okay, great. Well, thanks very much for that, Hadi. It's great to be here, and thanks everybody for joining. So it's my second time at the Hydrogen Summer School, and I'm providing a perspective on some lessons that we can take away from a lot of great work in carbon storage. So we have a few presentations generally in this topic this afternoon. I'll be talking about some of the more academic research we've been doing in the laboratory, in reservoir simulation, and fluid flow modeling. There will be other talks on the industrial experience and a really interesting discussion coming up here. So but I'd like to start with a high-level figure, actually, from the paper that Hadi just referred to, a review on underground carbon dioxide and hydrogen storage that we just published. And this figure is a really nice synthesizing figure comparing underground storage technologies, particularly hydrogen storage, carbon storage, and natural gas storage. And while, of course, I was very involved in the paper, this figure was really put together by Hadi, Sarah Gazda, and Jen Roberts. And it illustrates a number of really interesting things in the comparison. First and foremost, that hydrogen storage in comparison is much more similar, and I think we've been hearing this all day today, much more similar to natural gas storage than it is to carbon storage, if you have to give a kind of outright comparison. And you see that in the thermophysical properties. Here's a mass density profile of hydrogen and natural gas with depth. They're similar in magnitude and they're similar in character, whereas carbon dioxide goes through this transition point to a supercritical fluid. That also governs some of the constraints for carbon storage underground. It has to be greater than 800 meters or a kilometer in depth. That's not a constraint for natural gas storage or hydrogen storage, where you've seen the constraints are more about the lithostatic stress that maintains the cavern or aquifer integrity. Across the board, you can see a number of characteristics at different locations, so to speak, depending on whether this is salt cavern storage or porous media storage. And you see some of the horizontal bars here for the natural gas column and the hydrogen storage column very similar. So we have seasonal injection and production. We have cyclical loading. We're using salt caverns, depleted gas fields, or saline aquifers. Microbial contamination is an issue, and all of those things are similarities between natural gas storage and hydrogen storage, and not for carbon storage. There are a handful of cross-application commonalities, structural integrity, monitoring, concerns over seismicity, permeability, and storage or storable quantity estimates are all things required by these technologies. But by and large, the high-level comparisons are limited there. And so we've also heard that there are many unknowns around hydrogen storage, so it's not to say that hydrogen storage is exactly the same as natural gas storage, and we'll hear a lot more about those details in the coming days as well. But those are some of the key characteristics. So, but what I'm going to talk about are some of the lessons that we can take away from a lot of fantastic work and experience with carbon storage. This is mostly in the context of subsurface fluid flow. I'm showing here another schematic from that paper showing some of the reactive flow processes that take place and trying to put everybody as well on the same page, when we're talking about carbon storage, I'm referring to the capture of carbon dioxide, the injection of that carbon dioxide underground over 800 meters in depth into the type of geological formation that can trap that carbon dioxide. I'm not talking about mineralization in this case. And so that carbon dioxide will flow, it will be trapped, it will move in response to buoyancy, in response to heterogeneities. Sometimes it's used to recover oil with enhanced oil recovery. These are all flow processes that have been exhaustively studied and observed. So one of the key things I like to point out about this schematic is that these are not just flow processes of carbon storage as envisioned. This was carefully selected to exhibit carbon storage in the types of geological settings where it has been deployed today. So it is an early technology. There are around 30 to 40 projects, depending on how you count, but the variety of settings in which very large volumes of carbon are being injected underground is shown here. And so to that end, despite its early, its place as an early stage technology, it's fairly exhaustively demonstrated at large scales in a wide range of geologic settings, not to mention the various surface processes, the sources of carbon dioxide, and the industrial facilities used to capture, transport, and inject all of that. So in terms of the status of the technology, that's a bit of the positive. So with that context in mind, I'd like to go through 4 lessons that we can take from carbon storage, moving from the laboratory to the field. And firstly, for hydrogen storage in the subsurface, what I'd like to say is that the continuum framework for subsurface multi-phase flow is a good model of the physics. Okay? So this is an equation. We won't go through all of this, but it in many ways represents what will happen, that injection, the pressure-induced migration, the buoyancy, the impacts of heterogeneities. In many forms, they're all represented here in these terms. And when you have 2 phases moving through the subsurface, hydrogen and water, you need to parameterize the properties, not just with porosity and permeability, but also with multi-phase flow properties. The rate of flow and the ease of flow is governed not just by the absolute permeability, but a property called the relative permeability. The distribution of hydrogen in the subsurface will be controlled by a property called the capillary pressure. All of these exhibit hysteresis, and you can have trapping, immobilized hydrogen in the subsurface, and that's parameterized by a characteristic known as the residual trapping curve. And this is applicable across all of the subsurface fluid systems. So why do I point out this as being a lesson coming from carbon dioxide storage? Well, back in the late 1990s to early 2000s, there was a lot of ambiguity about whether this framework was appropriate for representing carbon storage. These properties were measured across a range of reservoir conditions, and they were seen to vary, and the continuum framework breaks down when that takes place. These things are supposed to be independent of reservoir conditions, but a lot of exhaustive research found that the breakdown or the apparent shift in the flow properties with reservoir conditions was caused by heterogeneity in the rocks. And as soon as the thermophysical flow properties of the fluids was accounted for, all of these observations could be explained. So here you see the distribution of carbon dioxide moving through rocks in this very heterogeneous manner. It upholds the integrity of the continuum flow modeling framework. The second lesson that we can take away is that the wetting state of these flow property systems is often a bit of a distraction. It's an ambiguity that is often used to hypothesize the outcome of difficult to interpret measurements in the laboratory. So wetting states do exist. We can have water wetting, we can have hydrogen wetting, we can have mixed wetting or intermediate wetting, but the measurements to determine that are very difficult and often imprecise. And as a result, the use of the ambiguity in the wetting measurement can often be used to hypothesize about ambiguity in measurements of flow properties. So this happened for carbon storage, and it created essentially 5 to 10 years of difficulty in pinning down how best to model the system. Happily, I think we're seeing a much faster coalescence for the hydrogen storage situation. So I'll point out a few aspects of the difficulty. So these are fairly advanced measurements showing a blob of, in this case, decane. It's non-wetting fluid, like carbon dioxide, like hydrogen. And you can see that it's non-wetting because the curvature of the blob against the surface of the pores of the rock is moving away from the rock. It's not spreading on the rock. If you make measurements of what the specific contact angle is, the main measure of wetting in the system, you can see that it's very noisy. This is an in situ measurement. If you make more historically conventional measurements on polished plates and crystal surfaces, you see a lot of noise as well in the measurement, and there are various reasons for that. There are robust signals arriving from the world of digital rocks. Our ability to look at the aggregate curvature of fluid phases in the pore space of rocks. So the underlying thermodynamic framework describing a multi-phase flow in the rocks essentially points to different signals that you could use in the laboratory, including interfacial fluid-solid area, interfacial fluid-fluid area, the contact angle, as has been typically used. And at this stage, you can pick and choose the most robust signals, so those are emerging. The fluid-solid surface coverage has emerged as the strongest measure of wetting because of the signal-to-noise basis and the thermodynamic theory supporting it. Okay, so to show you just how strong this is as a signal, we're just showing here, in this case, a non-wetting phase oil in a pore space otherwise filled with water. And you can see the little blobs of oil in the very crevices of the rock. If you plot the area fraction on an oil volume fraction graph, you get a kind of characteristic distribution of points, which describes to you the wetting state of this system. So this is an oil wetting state, and it means that even at low oil saturation, you'll have a relatively high fraction of the area of the mineral surface coated. So we have a clear signal of an oil wetting state, even in a part of the rock where you have very little oil. So this indicates the robustness of the signal. If we go to the other end of the spectrum where you have a lot of oil in the pore, you can see that the meniscus around the water is indicative of a system where the water is not wetting the surface of the pore, so you get this blob with the water instead of with the oil. And if you look at the intermediate case, you again see this very nice signal indicative of an oil-wet pore. So it's just to say, across the board, you can use this pore space imagery to very clearly tell you the wetting state of a rock. This is with oil and water. It's applicable to carbon dioxide and water. It's applicable to hydrogen and water. And as a result of that, we can apply these techniques with pore scale imagery of the distribution of hydrogen in rocks. So this is a publication that we had out just last year, led by the University of Edinburgh, in which hydrogen within the pore space of rocks was imaged at a synchrotron, and the distribution of the size distribution of the fluid blobs is very clearly indicative of a water wetting system. Okay. So the general lesson is that robust pore scale signals of wetting do exist, and they include the solid surface area coverage, the pore occupancy distribution, so on. We'll hear more about this tomorrow, but the body of literature is generally converging around hydrogen as a non-wetting phase. And coming back to the issue of carbon dioxide, the flow property measurements for carbon dioxide are unambiguous. It's non-wetting at reservoir conditions. So the wetting state as a distraction was the second lesson. Okay. So lesson 3, I've spent a lot of time looking at pore space imagery. This is coming from the realm of digital rocks. It's a lot of the kind of leading advance in subsurface flow often focuses in this realm. But right now, digital rock laboratory modeling techniques are useful for pore scale observations. There's a lot of very interesting and exciting work looking at hydrogen within the pores of rocks. And it's important to note that they're useful for pore scale observations, but they are still very uncertain and possibly inappropriate for the measurement of continuum scale properties. So relative permeability, capillary pressure, residual trapping, best measured in larger scale conventional core floods, imagery of fluid-solid interfacial area, pore size distribution of blobs, et cetera, connectivity of the fluid phases. These are the realms of digital rocks. And this is just emphasizing that, again, when we're wanting to measure directly the properties that are used in reservoir simulation, it is best done using very robust and well-developed techniques at larger scales than we're typically using for digital rock observations. Okay, and the final lesson that I'll cover brings us up a scale from the laboratory in the measurement of those properties, looking at how they're used. And one of the things that we've discovered with carbon storage is that carbon dioxide is very strongly impacted in its flow and in its trapping by very small scale heterogeneities. Centimeter to meter scale heterogeneities in reservoir systems actually control carbon dioxide flow. And it's a result of how multi-phase flow properties operate and serve to channel fluid phases through these heterogeneities in these systems. So I won't go through this in detail, but imagine this schematic as a centimeter thick layer with a high permeability and low permeability region. As a result of the way the capillary pressure and relative permeability curves work with fluid flow, when carbon dioxide and water are moving through these systems, because of the multi-phase flow properties, they're able to optimize their flow, leading to dramatic boosts in their mobility over what you would expect given conventional characterization and modeling. So the conventional approach would average over this, produce an upscaled property which doesn't account for this, but if you go through the painstaking process of characterizing and modeling fluid flow resolved at centimeter scales through these heterogeneous domains, what you see is that the carbon dioxide flow, in fact, can be factors of 2 to 4 faster in the system. If you bring that all the way, so that's the story with flow. There's an equivalent impact on trapping as carbon dioxide's moving upwards through a system. These small-scale heterogeneities can lead to an enhancement of trapping over what you would expect given the conventional way of characterizing and modeling reservoir simulations. So these impacts possibly underpin some of the challenges with field-scale modeling of carbon dioxide. At every single site where carbon dioxide has been injected deep underground, the carbon dioxide has migrated much more quickly and in directions that were unexpected, very difficult to model, very difficult to forecast, and very difficult to history match after the fact. So we've spent a lot of time developing techniques for upscaling the impacts of very fine-scale flow properties into field-scale models because we can't characterize the reservoir and we can't model the reservoir resolved at the centimeter scale, but we can come up with flow properties that allow us to do so at coarser scales in characterizing actual storage sites. So this is one of the target CO2 storage sites offshore United Kingdom, and it's a 4-way dip closure, very similar to exactly what we would be interested to use for hydrogen storage underground. Here we're looking in plan view at the sites, the simulations I'm about to show, place an injector, down dip from the site. This is more or less the plan for the storage concept here. For a hydrogen storage operation, you would be filling from the top but the injection and flow illustrates the impacts of these heterogeneities. So what we see is that at the outset, with carbon dioxide released at the bottom, the more heterogeneous reservoir baffles the carbon dioxide flow, and a lot of this will be trapped. After the plume gets to the caprock, it moves much more quickly laterally along the caprock as a gravity current, and the combined impacts mean you have a very different morphology and expectations about what will happen to the plume after it's injected than the conventional workflows for reservoir simulation provide you. So the dark red here shows more or less the conventional workflow with a gravity current spread out and a nicely coned distribution of carbon dioxide from the injection point to the caprock, whereas in practice what is happening from observations and what also happens in simulations that represent these impacts, you see a lot more spreading in the reservoir. This is intra-reservoir baffling, which leads to enhancements of trapping, and you also see a much thinner gravity current, which results in that carbon dioxide plume speeding well ahead of what was anticipated. So in the four-way dip closure, you would have essentially an opposite direction of the impact with hydrogen storage, but nonetheless, you do want to know things like how quickly will the hydrogen arrive at your management wells, how much of that hydrogen will be spread out throughout the system. Both of these impacts can benefit negatively or positively on projects if they're accounted for and incorporated into the management plans. So those are a few lessons that we have learned from the laboratory and in reservoir simulation for carbon storage, very applicable. And in fact, we're directly applying these to hydrogen storage. But at that stage, I'll end. And if there's any time for question or discussion, obviously, I'd be happy to answer any questions.
Fantastic, thank you. We have 10 minutes for questions. This is excellent, Sam. Thanks a lot for leaving room for it.
Thank you. Thanks, Sam. Okay. I'm Ipsita Gupta from Louisiana State University. Thank you for your talk. My question is for your upscaling of your pore scale properties. What kind of methods did you use for the different parameters? Were they same? Were they different? Were they same? And did you use any gas phase? And how did that impact your upscaling method? Thanks.
Yes. So for the upscaling, so I'll show this figure here. This shows essentially the porosity, capillary entry, and capillary entry pressure distribution, permeability distribution of a fully resolved grid block. So this is meters in height, so about 5 meters in height and 50 meters long for a grid block. And we use an invasion percolation based upscaling technique. So we essentially perform an analytic invasion percolation calculation on this grid block to identify the distribution of carbon dioxide and water in the grid block. It also includes the impacts of gravity. Once we do that, we can analytically estimate the relative permeability for each of the fluid phases, carbon dioxide or hydrogen, and water. And that's what we use to populate the coarser grid model. One of the things that arises is you get anisotropy in the relative permeability. So you get a relative permeability in the x direction versus the y direction, and I think you can start to see why that is the case looking at that.
Yes.
I have a question. A lot of these things you would also encounter or learn from gas flooding, the more traditional natural gas flooding of oil, for instance. Are there things that are specific for CO2 that are different from natural gas flooding?
I completely agree with that. We haven't applied this work to natural gas systems. We have seen a lot of papers that we think provide very strong anecdotal evidence that these issues are strongly impacting on natural gas systems, storage, and reservoirs that are being produced. The main differences will be primarily due to the thermophysical properties, but the viscosity of natural gas and the density is such that the impact should be even more accentuated for the natural gas system, and that's also what we expect for the hydrogen system.
Hey, Sam, I think one of the most important contributions your group has made is in the importance of heterogeneity and the unexpected upscaling properties. It's not simple spatial averaging. So I think that's critically important. I'm wondering, at the beginning when you had the plot that comes from your paper where you showed CO2 has very different thermophysical properties compared to methane and hydrogen. If you were to also think about a very big difference between CO2 relative to those two gases is solubility. Like, how does that change your thinking about how what we know about CO2 extends to hydrogen, which is, pretty much insoluble compared to CO2, which is so soluble? So I'm wondering how that shapes your thinking.
I think that is a big difference. So I'm not actually going to the slide that you were referencing, but to illustrate some of the major impacts that this has on carbon dioxide that won't apply to hydrogen. So in this case, for example, the baffling and the spreading and even the thin gravity current will dramatically enhance the dissolution of carbon dioxide in the reservoir. And that's a really positive thing. So one of it's a complicated story with carbon dioxide because of that. There are essentially counterbalancing impacts, whereas for natural gas or hydrogen, you won't have that. There are some estimates now, not from our group, but from Strom Neufeld's group at University of Cambridge, showing that with these configurations, you can have dissolution rates that are up to 10% of the injection rate of the carbon storage operation. But again, for hydrogen and natural gas, that is essentially null.
Evod was asking why I lose weight, and I said I run this conference. That's so it's
Bill Rawson, TU Delft. Question, if we could go back to your slide on the invasion percolation and the grid block. I usually think of the word grid block and invasion percolation in entirely different sort of universes. That invasion percolation is something I do on a network of bonds and nodes. It's, in a sense, it's almost not numerical, or in the same sense. How do you do invasion percolation in a numerical simulation?
Yeah, so each of the, so I referred to this whole block as a grid block because essentially this becomes the grid block of our upscaled model. But within this particular grid block, so while we're doing the upscaling, so within this particular model, there are a large number of small centimeter scale grid blocks. And so each of those grid blocks acts as a node in the invasion percolation algorithm. I should say that we're not the developers of so invasion percolation capillary limit type upscaling is established at least since the early 2000s. This particular upscaling approach combines both the percolation approach with the impacts of gravity. It makes it particularly suitable for use with carbon dioxide or hydrogen. It's developed by Wolf and Helmig, and a similar approach by Ali Niemu's group at nearly exactly the same time. So happy to refer you to those, and in any event, they're linked to in the paper here as well.
more questions. There's a question online about in a real hydrogen setting, we might have also cushion gas, and then it might end up with a three-phase system, which might be also not just hydrogen, it might be methane present and also brine. And how would be the framework to address this?
So I actually didn't address fully this is the question about gas injection in oil reservoirs. So that's a similar situation. And the answer is we haven't studied it. So these impacts of heterogeneity will be there in the hydrogen system or with carbon dioxide injected into oil reservoirs. They'll be even further complicated by the impacts of the presence of the third phase, whether that be through partial miscibility and dissolution and interphase mass transfer, or three-phase flow effects. We haven't studied that. I'm not entirely.
Nobody has studied for now the three-phase system. Any more questions? If not, let's thank Sam one more time.